All right, this is 14.3, wave behavior. We talk about what happens when a wave hits a medium. Talk about different types of interference and reflection and refraction. So when a wave hits a boundary, we're talking about the wave like a sound wave going from air to glass or from air to water. We can talk about a light wave doing the same thing. There's an example in the next slide about one spring being transferred into another spring. And these springs will have to have different spring constants. But some of the wave is transmitted to the next spring or the next medium. And some of the wave is reflected back in the opposite direction. Now these two waves, this transmitted wave and this reflected wave, should add up to equal the original wave. So these two waves should be the first original wave. Now the transmitted wave is also called the refracted wave. So if you'll hear me say refracted, that's what I mean. It's the one that goes through into the medium. Now, if the second medium is more rigid, so for instance, like I'm hitting the wall or a sound wave is hitting the wall, most of it is actually going to be reflected. So if the second medium is more dense, it's going to reflect a lot of that wave. And it's going to transmit less. And again, I don't see any cups, so if I don't see any cups, I'm going to keep moving. Here is an initial wave, or an incident wave. Incident and initial are the same thing here. And this wave goes through and it hits the next spring. So some of the wave goes to the next spring. That's the refracted or the transmitted wave. And some of it goes back, the reflected wave. If you add up the amplitudes, the tall parts here of each wave, it should equal this wave. Now here's a wave on a spring, and it hits a very dense medium, like a wall. And most of it is actually reflective, since it is so dense. And only some of that wave would actually end up going through here. Very, very, very small part, not causing much of it to shift. So superposition is what happens when two waves on a string or a line or the water, whatever your wave is going, when they add up together. They can either add or they can subtract. When they add up together, it's called constructive interference. So we have one wave and it hits this other wave that's the same height. They're actually going to double. So these two waves in phase are going to add up to equal a bigger wave. That's constructive interference. If you think about this with sound, it's like two people playing the same instrument and the same note. It's going to get louder. Destructive interference is when these two waves are out of phase. So we have one with a positive and one in the opposite direction. When they add up, since my top one is bigger, the top one is going to have a little bit more. But Think of this as a positive and this is a negative, so when they add up, they're subtracting, right? And yet, but just like a little tiny wave on the bottom. On the bottom, I mean on the top. And I just realized this stuff that's written on the board is not on the e-reader. So let me write this real quick. All right, so we have a wave with an amplitude, another wave with the same amplitude. They line up. When we add them up together, you're going to end up with a bigger wave. This one's constructive interference. Then our destructive interference, we have a wave on the top and then another wave on the bottom here. So when we add them up, I just drew this bottom wave pretty big, so could have go like this. So this one's destructive. You end up with a smaller amplitude wave. So brought me this. Do you have your homework too?
I have the past 2 days, Tuesday and Wednesday, that's when I call my lessons.
You don't need a homework password when you're absent.
Okay.
You only need one for the 14-15 outline.
Yeah.
Okay, so here's some pictures. Now these, this slide's a little difficult to read. You're actually going to go straight down. So at the top here, we have a wave going to the right and a wave going to the left. And they're out of phase. One's on top and one's on bottom. So when they hit together, they cancel. And then after they have interacted, this is your superposition right here. After they've interacted, they have momentum, right? Momentum is mass and velocity. You have your momentum, your marbles, you have 3 on this side, 2 on this side. When they transfer, you're going to end up with 3 on this side and 2 on this side going this way. So just like that, momentum, like that Newton's cradle, your wave is going to continue to go left. So this one keeps going left and that one keeps going right. So they end up, so they only interact with each other when they're right over top. This one over here is a constructive wave, so we have 2 waves going together, and then they add up. So this is the original height of each one, and they add up to equal your total amplitude. And then they keep going. And here's one. We have a big one on top and a little one on the bottom. They interact, and you end up with just a little bit on top. And then they keep going. So you still have the little going left and the big one going right. So here's a clicker question for you. Don't get excited, we're not finished yet. It says, which is not an example of interference? This one's a little bit difficult. Think about which one is not adding energy to it.
This is a clicker question.
It is a clicker question, yes. Listen, 5 people. Okay, I'm not going to wait anymore. Here we go. The only one where it's not adding energy to it is actually a bumper car, because that is an example of reflection. A bumper car is just hitting it and coming back. The wall's not adding any energy to it. The basketball is interference because you're adding energy to it. You're hitting it with your hand at regular intervals to increase the height of it or to keep it going the same height. This is a pendulum, right? The child swinging is a pendulum. So you're adding energy in order to get the child to get higher and higher. And a guitar string, if you pluck it once, if you pluck it repeatedly, you're continually adding energy to it. And you're going to do it at pretty regular intervals to keep it going. All right, the bumper car is the only thing that doesn't actually, it's not added energy. It's also not going wet. Guitar is because it's, well, it's a, first of all, it is a wave vibrating back and forth. And you're continuing plucking it, so it's continuing to move on. You're adding amplitude to it the more you pluck it. All right, standing waves. Standing waves are stuck. They have nodes at each end. The best example of this would be your guitar string, right? We were just talking about. Your guitar string is stuck at each end, so when we pluck it, it vibrates. Where it's stuck at equilibrium, that's a node. And the opposite, the highest or lowest amplitude, is antinode. Now you can get more and more waves on this string, like this. And each one of these is a node. And each one of these is an antinode. I can do this with my slinky. It doesn't look real great, but there we go. So there's a standing wave. And then if I shake it back and forth even more, you can kind of start to see all the other little waves. I'm just really bad at it. There we go. So you can see there's a couple more half waves in there. Sort of. All right, here's a picture of some standing waves. This is like a guitar string right here. So you have a node on each end and an antinode in the middle. This one, when we get to sound, is actually known as the fundamental frequency because it's the biggest wavelength, which means the smallest frequency that you can get on this particular instrument, if this wasn't it. And we can add more energy to it, a higher frequency, and get more of these wavelengths on here. But the wavelengths get shorter. So this one went from, this is half a wavelength, right? And then we have 1.5 wavelengths. And we have 4 nodes, right? 1, 2, 3, 4, and 3 antinodes. And then the bottom here, we have 1, 2 wavelengths. So this one's a higher frequency, shorter wavelength. And we have 1, 2, 3, 4, 5 nodes. and 4 antinodes. And something that's interesting about standing waves is that, notice they're always in intervals of half a wavelength. So here we have a half a wavelength, here we have 1.5, and here we have 2. So on a standing wave, you can only have half, 1, 1.5, 2, 2.5, and so on. You can't have a quarter of a wavelength, not on a standing wave string like this. You can't have a quarter, or you can't have a third. You can't have a sixth. It has to be half, 1, 1.5. It has to be something like that. It has to be an interval of half of a wavelength. And that's something that we'll encounter when we do the next chapter. You'll see that, why that's important. Two-dimensional waves. These are one-dimensional waves. All the stuff that we've been dealing with, this standing wave stuff. What's on the board up here, that's all one-dimensional waves. The two-dimensional waves, like a water droplet, or this little object here that's creating regular intervals of waves, comes out in a circle. So it propagates across the top of the water in a circle. Now if we draw this pattern on a piece of paper, you can either pick the very tops of the waves or the very bottoms of the waves, whatever you want to, in order to draw the diagram below it. And we call this line that we're using to represent the wave a wavefront, and that is supposed to represent the crest of the wave, the highest one. And you can find the wavelength from this diagram by measuring between two wave fronts. So from crest to crest, just like normal. So if they propagate out in a circle in 2 dimensions, what would they be if we did it in 3 dimensions? A circle in 2 dimensions, what would it be in 3 dimensions? A sphere. There we go. Just like sound is going, so I'm emitting a sound right now, and it is going up and down and outwards all at once. The pressure wave like a giant sphere. Same thing with light. Light does that, like a light bulb is emitting it in all dimensions. The next one we're going to talk about is reflection. So when a wave hits a medium or a boundary, let's think about this as like air, and this is water down here. So you have like a sound wave or a light wave is coming in and hitting the surface of this water. So this vector right here is called a ray. And that is going to have some sort of magnitude, so some sort of, maybe a wavelength of energy or whatever it is we're talking about. And you can see its direction. So the law of reflection says that as measured from the normal, which is perpendicular from the surface, so the normal is always like straight up, that's just like the normal force. And you're going to measure it, the angle of the ray between the normal and where it's coming in. The law of reflection states that it's going to be the same angle on the other side of the normal. This is how people get so good at pool, because it always reflects with the same angle. So if you hit it with a wide angle, so like way over here, it's going to come out way over here with a wide angle. If you hit it with a very narrow angle, it's going to come out with a very narrow angle. But it's always measured to that normal. Okay, refraction. So remember, all waves, when they change mediums, so like from our air to our water, are going to both reflect and refract. So this is the refraction part, the transmitted part, the part that goes into the medium. And there's actually a law for this. It's called Snell's law, which we're going to cover in chapter 18 or 17, I can't remember which. And it's going to change its speed and it's going to change its angle because it's going through either a denser or a less dense medium. So when it does that, it ends up shifting a little bit and either slowing down or speeding up. So you're still using the same incident angle, the same initial angle from the normal. But now the wave is going to go through on the other side of the normal, and it'll either be closer to the normal or further away, depending on the density of the second medium. All right, and then after this, I have 2 more clicker questions for you, and then we're finished.
So we're done with those.
All right, here's your first clicker, or your second clicker question. We have one there. It says, tapping the surface of a pan of water generates 17.5 waves per second. If the wavelength of each wave is 45 centimeters, what is the speed of the wave? Now, if you can't remember how to solve this one, yesterday I taught you an equation, wavelength over frequency, and then if you need these, just in case.